we're going to jump straight into section 6.2 with an example. 6.2 will finally be the simplex method. We're going to introduce the simplex method, how it works, and how to solve standard maximization problems of standard form. So what I have behind me is exactly one of these things. Notice this is a maximization problem that's in standard form. I've got my non-negative constraints. All of my inequalities here are less than or equals to, and on the right hand side we have non-negative numbers. So this is a standard maximization problem in standard form. And the simplex method is a fairly long algorithm, so we're just going to sort of go through this as it comes. But here's step one. Step one is construct what's called the initial system. Construct the initial system. So there's two pieces to this. One is I want to take my I system right here and convert this to an E system. So I need to introduce slack variables. I'm going to have 4x1 plus x2 plus some slack variable s1 is equal to 28. And I've got 2x1 plus 3x2 plus some other slack variable s2, let's put the plus over here, is equal to 24. So there's the associated E system for this I system. And there's one more thing I have to do, and the order here matters, so you put the E system first, and then down below it there's one more thing. You take your objective function and you rearrange it. So I want P to be positive, but I'm going to move everything else to this side. So we've got minus 10 x1 minus 5x2 plus P equals 0. Alright, so this is the initial system. You take your I system and you convert it to an E system by introducing slack variables. And then at the bottom here, you take your objective function, you leave P positive, so you don't want to move P to this side. You leave P on this side, and you subtract everything else. So P ends up being positive. We've got all of these expressions over here as negative, and that all equals 0. And this is the so-called initial system. Step 2 is now, once I have my initial system, now I construct the simplex, I believe it's called the initial simplex. Initial simplex tableau. Okay, and the way we do this is we're going to build a matrix. So we're going to build a matrix where my columns are the coefficients of everything that's appearing in the system. So my first column are going to be the coefficients of x1, and typically you label these to keep track of things. So x1, my coefficients are 4, 2, minus 10. Then I've got x2, my coefficients are 1, 3, minus 5. x2, 1, 3, minus 5. Then I've got s1, my coefficients are 1, 0, 0. 1, 0, 0. Then I've got s2, my coefficients are 0, 1, 0. And then we've got p, my coefficients of p are 0, 0, 1. And then we've got everything to the right-hand side of the equals bar. We've got 28, 24, and 0. 28, 24, and 0. And that's the whole matrix. Now it's customary to augment this, just like we'd usually do with an augmented matrix. So here's my equal sign. I've got an augmentation bar there. And it's also customary to separate off this objective function down at the bottom from the E system above it by a dash line. So we'll introduce a little dash line there. And there's my initial simplex tableau. There's one more thing that we have to do though. We have to put labels on the rows as well. And the way you do this, again, this is just the algorithm, is assuming my first row here corresponds to the equation with the slack variable s1, I label this s1. And the second row is the equation associated to the slack variable S2, so I'm going to label that slack variable S2. And then customarily down below this is the objective function with p in it, so I'm just going to label that as p. And now we've constructed the so-called initial simplex tab level. So lots of notation here, but it really is just a coefficient matrix with an augmentation bar for the equality sign, and columns are labeled as usual, telling us which variables these are coefficients for. But then over here, I've just got the rows labeled as well, S1, S2, and P. Okay, so there is the initial simplex tableau. Now we're going to do row reduction. So, how much space do I need? I'm going to erase most of this. Perform a pivot operation. Alright, so what is a pivot operation? Well, there's quite a few steps to this. I'm actually not going to write them down. We'll talk about this. But here's what we need to do. We need to decide on a pivot entry. How do I decide on that? Well, the pivot entry is going to be the intersection of a pivot column and a pivot row. So how do I decide what a so-called pivot column is? Well, I look down at the entries down here in my P row, and I choose the most negative value. So the negative value that's the furthest away from 0, here I've got -5 and -10. The most negative value is -10. So this is, how about I circle everything here. This is my pivot column. Okay, so there's the first step. You just look at the most negative number and you say, okay, this is my most negative number, -10, so that's going to be my pivot column. The second thing I have to do is decide on a pivot row. And what I do here is I look at the entries above the dashed lines, so I've got 4 and 2. I take the corresponding entries in the same row to the right of the augmentation bar, and I divide them by these entries. So here I'm going to do 28 over 4. 28 over 4 is 7. And I've got 24, I'm going to divide that by 2. 24 divided by 2 is 12. Whichever one of those gives a smaller value is my pivot row. So 7 is smaller than 12, so this is my pivot row. Alright, so this is smaller. That's why this is my pivot row. And my pivot entry is the entry that's in the pivot column and the pivot row. So that guy right there, 4. There's my pivot entry. And what I'm going to do is, the first thing I'm going to do is I'm going to rescale this to a 1, and then I'm going to use it to zero out everything in the column with it. Alright, so first thing we do is we rescale it to a 1, so I just want to divide all of row 1 by 4. So 1/4 row 1 is going to become our new row 1, right? We're doing Gauss-Jordan elimination, so same notation as usual. Let's see, divide this row by 4, I've got 1, 1/4, 1/4, 0, 0, 28 over 4 is 7. And the other two rows should be exactly the same. 2, 3, 0, 1, 0, 24, -10, -5, 0, 0, 1, 0. Alright, and now that I've rescaled it to 1, now I use it to zero out everything else below it. So, let's see, what do I want to do here? I want to subtract twice the first row from the second one, so we'll do row 2 minus 2 times row 1 is going to become our new row 2, and we'll add 10 times the first row to the last row. So row 3 plus 10 times row 1 becomes our new row 3. And going through this process, well, it's just Gauss chart on, so let's see what we get. Copy down the first row 1, 1/4, 1/4, 0, 0, 7. Okay, so we're going to add 2 times the, no, we're subtracting, sorry. We're subtracting 2 times the first row from the second, so 2 minus 2 times 1 is 0, just like I wanted. 3 minus 2 times 1/4, that's 3 minus a half. 3 is 6 halves, so 6 halves minus 1/2 is 5 halves. 0 minus 2 times 1/4, so that's minus 1/2. 1 minus 0 is 1, 0 minus 0 is 0. 24 minus 2 times 7, 24 minus 14 is 10. Now we've got our last row here, and we're adding 10 times row 1 to it, so minus 10 plus 10 is 0, just like I wanted. Minus 5 plus 10 times 1/4, what is that? 10 times 1/4 is 10/4, this is minus 20/4, so that should be minus 10/4. I'm just going to check against my numbers as we go through this. And how about I simplify this as we go as well? So instead of minus 10/4, I'll write that as minus 5 halves. 0 minus 10/4 is minus 10/4, or minus 5 halves. Actually, this is why I'm checking my notes. It's very easy to make mistakes while you're doing this, so be careful to double check. I was minusing in my head. We're doing plus, right? It's row 3 plus 10 times row 1. So 0 plus 10 times 1/4 is plus 10/4, or plus 5 halves. 0 plus 10 times 0 is 0. 1 plus 10 times 0 is 1. 0 plus 10 times 7 is 70. And like I said, let me just check this against my notes very quickly, make sure I'm happy with that we haven't made any mistakes. And so far so good. So there's one more thing that we have to do. This is the end of the pivot operation, but there's one more thing that I have to do. You'll notice I've been a bit lazy. I haven't been labeling my my columns. So let's relabel these: x1, x2, x3, x4. Oh, sorry, it wasn't x4. It wasn't even x3. This was our slack variable s1, s2, and p. Okay, so tiny bit more notation or terminology. The entry in the column, or the variable corresponding to the pivot column, this is usually called the entering variable. And the variable in the row corresponding to the pivot row, this is usually called the exiting variable. Right? The way this plays out, and hence the names, at the end of my pivot operation, when I'm done with everything, I'm going to replace my exiting variable with the entering variable. So this is still x1, x2, s1, s2, and p up here, but s1 gets replaced by the entering variable. So this is now x1, and then s2, and p. Important to keep track of this as we go, because we're going to use this to read off our solution at the end. And everything we've done so far here in step 3, this is the bulk of the simplex method. So just to recap, pivot operation, you do quite a few things. You decide on a pivot column. The way you decide is you look at the most negative number down here. That's your pivot column. Then you look at the entries above the dash line. You look at the entries above the dash line, and you take those entries and you divide them into the entries to the right of the solid augmentation bar here. You divide them into these entries, and you look at which one is smaller. The smallest value that you find gives you your pivot row. All right, so this was our pivot row. The intersection of the pivot column and the pivot row is your pivot entry. I suppose there's one thing I didn't mention here. What happens if you get a 0? Right? What if one of these entries is 0? How do you divide these numbers by 0? Well, you don't. All right, so you can't do that. And if an entry is negative, you also skip it over, right? So we're only working with non-negative entries as we do this. We don't look at the zeros, we don't look at negative entries, which could happen. And one more thing you might say is, what happens if they're all 0 or negative? Well, it turns out that in that case, you can stop. The simplex method tells you right then that an optimal solution doesn't exist. All right, so if all entries are less than or equal to 0, no optimal solution exists. And we'll actually look at an example like that. I want to show you sort of how that works. But in this case, we had lots of positive entries, so we're able to divide them into the stuff to the right of the augmentation bar, and look at which one is smaller to get our pivot. Once you have the pivot, you do two things. You rescale it to a 1, and then you use that entry to zero out everything in the column. All right, so that's what these two row operations were. And the last thing you do is you replace your exiting variable with the entering variable. All right, so you just look at your entering variable, it's the variable corresponding to the pivot column, and you plug that in to the variable that used to correspond to the pivot row. All right, so there's a pivot operation. And now, step 4 is repeat step 3 until you no longer have any negative numbers down here. All right, so step 4, repeat step 3 until no negatives in bottom row. Or until you run into a point where you can conclude that an optimal solution doesn't exist. All right, so I've only got one more negative in my bottom row. It's minus 5 halves, so we're gonna go with that. So minus 5 halves. So I know that's the only one, right? So this is the most negative number. So here's my pivot column. Now I have to decide what my pivot row is. So I divide 1/4 into 7, and I divide 5 halves into 10, and I look at which one's smaller. So 7 over 1/4, well, that's the same as 7 times 4, which is 28. And 10 over 5 halves, that's the same as 10 times 2/5. 10 times 2/5, let's write it down, 10 times 2/5. 5 goes into 10 twice, so that's 2 times 2, which is 4. 4 is smaller than 28, so this is my pivot row. Which means what I really care about is that there's my pivot. There's my pivot entry. So I want to rescale this to a 1. I need to multiply the entire row by 2/5. So we'll do row 2, we'll do 2/5 of row 2, will become our new row 2. 1, 1/4, 1/4, 0, 0, 7. Just copying down the first row. Second row, we're multiplying it all by 2/5. So we're going to have 0, 1, 2/5 times minus 1/2 is minus 5. 2/5 times 1 is 2/5. 0 times 2/5 is 0. 10 times 2/5 is, as we just saw, 10 times 2/5 is 4. And the last row I haven't done anything to. This is 0, minus 5 halves, 5 halves, 0, 1, and 70. Some people continue to label their columns and rows as they proceed, but just like I did over here, I'm just going to do that as sort of my last step. So let's see, I'm going to erase I'm just going to erase this. And I just checked against my notes. I have a mistake here. My mistake here is popping up right here, -5. Why is that a mistake? 2/5 times -1/2. 2/5 times -1/2 is not -5. That is -1/5. There we go. -1/5. Okay, so now I want to use this entry to zero out everything above and below it, right? Everything in the column. So how am I going to do that? Well, I want to do row 1 -1/4 of row 2. Row 1 -1/4 of row 2. And we want to do row 3 plus 5/2 of row 2. Plus 5/2 of row 2. Okay. So row 2, let's just copy down row 2 really quickly because that's the one we're not going to mess with. 0, 1, -1/5, 2/5, 0, and 4. Okay, so we're doing row 1 -1/4 of row 2. 1 -1/4 of 0 is still 1. 1/4 -1/4 times 1 is 0, just like I wanted. 1/4. What is this? This is 1/4 minus 1/4 of -1/5. So that's actually 1/4 plus 1/4 times 1/5 is 1/20. Putting this over 20, multiply top and bottom by 5. Gives me 20 there, 5 here. That is 6/20 or 3/10. 3/10. Okay, we've got 0 minus 1/4 times 2/5. 1/4 times 2/5 is 2/20 or 1/10, so that's -1/10. 0 minus 0 is 0, and now I've got 7 minus 1/4 of 4. 1/4 of 4 is 1, so 7 minus 1 is 6. That looks okay. All right, unfortunately, as fractions here, you have to double check all of these calculations. They can be kind of messy, but we'll do the same thing in the bottom row. I've got row 3 plus 5/2 times row 2. 0 plus 5/2 times 0 is 0. Minus 5/2 plus 5/2 is 0, just like we wanted. 5/2 plus 5/2 times -1/5. 5/2 times -1/5 is -1/2. So 5/2 minus 1/2 is 4/2, or just 2. 0 plus 5/2 times 2/2. 5/2 times, 5/2 times 2/5 is 1. So 0 plus 1 is 1. 1 plus 0, 1. And 70 plus 5/2 times 4. 4 times 5 over 2 is 20 over 2, or 10. So this is 70 plus 10, which is 80. Again, check all these fractional calculations if you want, but we're just going through these row operations that we've done many times. And I'm going to relabel my columns, x1, x2, s1, s2, and p. And we have x1 here, but s2 is my exiting variable. My entering variable is x2, so I'm going to replace s2 with the entering variable to get x2 and p. The good news is we're done. It's a fairly long process, but we're done now. Step 5. Well, step 4 would be repeat again if I've got more negatives down here, but I have no negatives left. So step 5 is just read off the solution. Step 5. Read off the solution. So what does this tell me? This tells me all I have to do to read off the solution is take my variables over here, x1, and equate this with everything to the right of the augmentation bar. So x1 equals 6, x2 equals 4, and my maximum profit is going to be 80. P equals 80. So that's it. It's actually really nice. Once you've reduced it to this form, it's very easy to read off your solutions. This is why you have to keep track of your entering and exiting variables as you go, so that you know what variables these numbers are corresponding to. But this tells me x1 is 6, x2 is 4, p is 80, and everything else that doesn't appear over here, everything else is just 0. So my slack variables s1 and s2 are both 0. So we don't have any excess here. There's no slack. This sort of perfectly maximizes the inequalities. That's the simplex method. We're going to go through several more examples. I want to show you sort of what roadblocks you can run into. So we'll do a few more, but this is the whole algorithm. All right, so let's look at another one. Here we have a standard question, solve using the simplex method, a maximization problem. I'm going to check really quickly that it's in standard form. Well, we're asked to maximize, so it's maximization. Standard form, I have non-negative constraints, that's good. Everything is less than or equals to, that's good. And everything to the right of these less than or equal to signs, all of these constants over here, those are non-negative. So this is indeed in standard form. So I know the simplex method applies, and we're going to go ahead and apply it. So just going through all the steps from last time. Step 1, build the initial system. What do I have to do? I have to replace my I system with an E system. So I'm going to have minus 3x1 plus 4x2 plus some slack variable s1 is equal to 12. I've got x2 plus some other slack variable s2 is equal to 2. And then last but not least, once I've got my my E system, below that I take my objective function where I've left p as positive, but I've moved everything else to that side. So I've got minus 2x1 minus 3x2 plus p equals 0. Alright, so I just rearrange this equation, set it equal to 0, but do it in a way where p is positive. Alright, so there's my initial system. Then step 2, let's just do this right here. Step 2 is build my initial simplex tableau. How do I do that? Well, my columns are the coefficients of the variables. So the x1 column, coefficients of x1, minus 3, 0, minus 2. x2 column, coefficients of x2, 4, 1, minus 3. s1 column, coefficients of s1, 1, 0, 0. s2, I've got 0, 1, 0. P, I've got 0, 0, 1. Augmentation bar 12, 2, 0. We'll dash off the last row as we usually do. And we'll label our rows. First row corresponding to slack variable s1, second row corresponding to slack variable s2, and p. Okay. Now that we've built the tableau, now we start doing our pivot operations. So, how does this work? Well, I have to decide on a pivot column. I look down here and I find my most negative number, minus 3. There's my pivot column. I take the entries above the dash line, 4 and 1. I can only take positive entries here, but they both are positive. And I divide them into the corresponding entries in the same row to the right of the dash line. So I don't have a whole lot of space, but 4 into 12, so 12 over 4 is 3. And 1 to 2, so 2 over 1 is 2. And I choose the smallest value. So which one's smaller, 3 or 2? 3 is smaller. Or sorry, 2 is smaller. So this is my pivot row. And the intersection of the pivot row and pivot column, which is that entry right there, there's my pivot entry. Now I have to do two things. I have to rescale it to be a 1. Well, that's already done, so that's good. And then I have to use it, Gauss-Jordan elimination, use it to zero out the entries in the column that it belongs to. So how am I going to do that? Well, I'm going to subtract 4 times row 2 from row 1. So row 1 minus 4 times row 2 becomes our new row 1. And we're going to add 3 times row 2 to row 3 to get a 0 there. So row 3 plus 3 times row 2 becomes our new row 3. Okay, let's just copy down row 2 really quickly. 0, 1, 0, 1, 0, 2. And we'll go through our row operations. So row 1 minus 4 times row 2. Minus 3 minus 4 times 0 is still minus 3. 4 minus 1 is 0, just like I wanted. 1 minus 4 times 0 is 1. 0 minus 4 times 1 is minus 4. 0 minus 0 is 0. 12 minus 4 times 2, 12 minus 8 is 4. And bottom row here, row 3 plus 3 times row 2. Minus 2 plus 3 times 0 is minus 2. Minus 3 plus 3 times 1 is 0, just like I wanted. 0 plus 0 is 0. 0 plus 3 times 1 is 3. 1 plus 3 times 0 is 1. And 0 plus 3 times 2 is 6. Cool, so there's the row operations done. And there's one more thing to do. Remember, I have to decide on my exiting and entering variables and replace them. So what do I have? x2 is my entering variable, s2 is my exiting variable, so I replace s2 with x2. So I've got x2 here, and I still have s1 and p. There's the pivot operation complete. By the way, one more thing I want to point out is as we go through these pivot operations, as we make everything down here non-negative, you'll notice that I started off with p and a 0 over here. Now I've got p and I've got a 6 over here. And remember that when we're done, this is going to correspond to my maximum value for p, the maximum profit if you want. So notice that as we go through these pivot operations, this is always increasing. It increases until you're done, until you don't have any negatives left, and then you have your maximum value for p. So it is getting bigger all the while. And I still have minus 2, so we have to do a pivot operation again. So this is the most negative number. It's in fact the only negative number. So here's my pivot column. And I decide on the pivot row by dividing these entries into the numbers to the right of the augmentation bar, but I run into a problem. What's the problem? The problem is that minus 3 is negative, or at least it's not positive, and 0 is not positive. So we unfortunately can't carry on with the algorithm because we're only allowed to divide positive numbers into these things and look for the smallest value. What happens if I can't do anything, if I don't have any numbers to proceed with? It means there's no optimal solution. All right, so no optimal value. All entries are less than or equal to 0, so that means there's no optimal solution. And we're done with the problem. There's nothing else to be done here. Remember, this can exist, right? This can exist. Go back to last time. This is in fact something you can solve with the geometric method from last time. There's only 2 variables in this problem. If you do this, you'll look at your feasible set, your feasible region, and you'll see it's an unbounded region. So there is actually no maximum value. Alright, so if you tried to solve this geometrically, you would have reached the same conclusion, and probably a little bit faster, to be honest. But we'll keep going. So here's a typical word problem. It's going to be the last example we do in this section. I'm not sure we've done quite enough of these to really move on yet, but the good news is the next section is essentially doing the same thing. So if you want to see more examples of using the simplex method, well, we're going to do it again in 6.3, so there will be more examples here. So we'll just do one more. It's a word problem, meaning I've got to take this real-world application, these words, convert it to a mathematical system or a mathematical model, and then we'll be in business. We'll be doing exactly what we just did using the simplex method. So here's what we have. A department store has up to $20,000 to spend on television advertising for a sale. All ads will be placed with one station, and we're given some pricing here. A 30-second ad costs $1,000 on daytime television, and it's viewed by 14,000 potential customers. Costs $2,000 on primetime television, viewed by more customers, 24,000 potential customers, and $1,500 on late night TV, viewed by 18,000 potential customers. There's some constraints here though. The TV station will not accept a total of more than 15 ads in all 3 time periods. How many ads should be placed in each time period in order to maximize the number of potential customers who will see the ads, and in that case, how many potential customers will see the ads? So I need to construct a mathematical model for what's happening here. And the first thing I have to do is decide on my decision variables. What am I trying to decide on? Well, I'm trying to decide on how many ads I should run in daytime television, how many ads I should run in primetime television, and how many ads I should run in late night TV, right? That's what I'm deciding on. So let's let x1 be the number of ads. Let's call it number of daytime ads. We'll let x2 be the number of primetime ads. And x3 be the number of late night ads. Those are my decision variables. That's the only decisions I'm making. How many ads am I going to run in the daytime, how many in prime time, and how many late night. What do I want to maximize? I want to maximize the total viewership, the total number of potential customers who see the ads, right? Well, what's that going to amount to? If I run x1 daytime ads, how many people are going to see it? If I run x1 daytime ads, for every daytime ad you run, 14,000 people see it, right? So it's going to be 14,000 times x1. We're going to make a lot of simplifications here. I'm going to ignore things like repeat viewership. I'm going to assume every time it runs, this is 14,000 new people seeing the ad. Unlikely, but we have to simplify in this way. We're also not doing things you would usually do, like demographic considerations and so on. We're just trying to reach the most number of eyes as possible. So I've got the number of people that view the ads are going to be 14,000 times the number of daytime ads I watch or play, plus for every primetime ad, 24,000 times x2, and plus the number of late night ads, 18,000 times x3. That's what I want to maximize, but I have some constraints here. One constraint is my money. I've only got 20,000, right? So if I run x1 daytime ads, the cost of that is going to be x1 times $1,000, right? So subject to 1,000 times x1 plus 2,000 times x2 plus 1,500 times x3. That's the total amount I'll be spending, right? $1,000 per daytime ad, $2,000 per primetime ad, $1,500 per late night ad. So add all three of those expressions together. That has to be less than or equal to the $20,000 that I can spend. And I have one other constraint. I have another constraint in that the TV station won't accept more than a total of 15 ads. Right, so I also need x1 plus x2 plus x3. I need that to be less than or equal to 15. Do I have any other constraints? That should be it. That's my only constraints. But I also, I obviously can't run a negative number of ads, so I also have my non-negative constraints that x1, x2, and x3 are all non-negative, bigger than or equal to 0. So I've taken all of these words, this word problem, and I've converted it to a mathematical model. I have a function that I want to maximize, given some constraints, and this is a standard maximization problem in standard form. Everything's less than or equal to, these numbers are both non-negative, so the simplex method applies, and now I just have to apply the simplex method to this problem. Alright, so what's my first step? First step is create the initial system. Alright, so I've got 1,000 x1 plus 2,000 x2 plus 1,500 x3 plus some slack variable s1. That has to equal 20,000. I've got x1 plus x2 plus x3 plus some other slack variable s2. That has to equal 15. There's my E system, and now I take my objective function and I move everything to the left-hand side, so P is positive. So minus 14,000 x1 minus 24,000 x2 minus 18,000 x3 plus P is equal to 0. There's my initial system, and using this initial system, I build my initial simplex tableau. Alright, so we build the initial simplex tableau. X1 column, I've got 1,000, 1, and minus 14,000. X2 column, I've got 2,000, 1, and minus 24,000. X3, 1,500, 1, minus 18,000. Then we've got S1 is 1, 0, 0. S2, 0, 1, 0. P, 0, 0, 1. And then we've got 2,000, 15, and 0. And I'm going to put a dashed line here. And I'm going to label these. This is S1, S2, and P. There's my initial simplex tableau. One more thing I want to point out is you might be tempted to, because these numbers are pretty big, you might be tempted to rescale these equalities, maybe divide both sides of this by 1,000 or something. It's doable if you really know what you're doing, but then in the next section, 6.3, you really shouldn't be doing that. So my advice is just don't rescale anything. Just leave it as it is. Even if the numbers are pretty big, this problem isn't too bad. Alright, so there's my initial simplex tableau. I unfortunately should have left myself a bit more space, but now we go through and we do our pivot operations. Alright, so I look for the most negative number, minus 24,000. That's more negative than minus 14, minus 18. So here's my pivot column. And I take these two numbers, 2,000, and divide them into these numbers over here, right? So 2,000 over 2,000 is 1, and 15 over 1 is 15. Which one of those numbers is smaller? Obviously 1, so this is my pivot row, and there's my pivot entry. So like I said, I really wish I left myself more space here. I don't really have room below to work with this, so I'm just going to have to squeeze it in above, I think. But the first thing I'm going to do is I'm going to divide the first row by 2,000 to scale this to a 1. Alright, so divide the first row. 1 over 2,000 times row 1 becomes our new row 1. $1,000 over 2,000, 1/2. 2,000 over 2,000 is 1. 1,500 over 2,000, that's 1.5 over 2. I should rescale that. That 1.5 over 2 is 3/4. 1 over 2,000 is unfortunately just 1 over 2,000. 0, 0. 2,000 over 2,000 is 1. One, 1, 1, 0, 1, 0, 15. Minus 14,000, minus 24,000, minus 18,000, 0, 0, 1, 0. I don't usually relabel these things as we're going right now, but I'll just indicate this is the X2 column, and here I've got S1, S2, P. And I'm just labeling those because I have to erase them. My mistake already is actually fairly significant. The original number here, I believe I had wrote 20,000, or sorry, I wrote 2,000. That original number should have been 20,000, right? That was the number, the maximum number of money we can, maximum amount of money we can spend is $20,000. So that should have been 20,000. I wrote 2,000, so I don't believe it affected anything. If we did 20,000 over 2,000, that's 10, which is still smaller than 15 over 1 was. So we still chose the correct pivot. Thankfully that didn't make a big mistake for us. But 20,000 divided by 2,000 is not 1, that is 10. So I'll just fix that right now. Sorry about that. But what I want to do, so now I want to take my pivot and I want to zero out everything below it, everything in the same column. So we're going to do row 2 minus row 1 becomes our new row 2, and we're going to do row 3 plus 24,000 row 1 becomes our new row 3. And I'm going to put this way down here so I have enough space in the future. Row 1, I'll just copy down row 1 again. It's 1/2, 1, 3/4, 1 over 2,000, 0, 0, and 10. Right, not 1, 10. And yeah, so now we're going to proceed. Row 2 minus row 1. 1 minus 1/2, 1/2. 1 minus 1, 0, just like I wanted. 1 minus 3/4, 1/4. 0 minus 1 over 2,000 is minus 1 over 2,000. 1 minus 0 is 1. 0 minus 0 is 0. 15 minus 10 is 5. Awesome. And now we're down to row 3. Row 3 plus 24,000 times row 1. 24,000 times 1/2 is 12,000. So minus 14,000 plus 12,000 is minus 2,000. Minus 24,000 plus 24,000 is 0, just like I wanted. Minus 18,000 times 24,000 times 3/4. What is 24? 24,000 times 3/4. 24,000 divided by 4 is 6,000, times 3 is 18,000. So I've actually got minus 18 plus 18,000 is 0. Alright, what else? I've got 0 plus 24,000 times 1 over 2,000. 24,000 over 2,000 is 12. So 0 plus 12 is 12. 0 plus 24,000 times 0 is 0. 1 plus 0 is 1. 0 plus 24,000 times 10 is 240,000. Alright, row operation successful. One more thing to do. X2 was our entering variable, S1 was our exiting variable, so let's just relabel these really quickly. X3, S1, S2, P. We replace S1 with X2. X2, S2, and P. Awesome. Something really lucky happened here. Not only did we zero this entry out, we also got rid of another negative. This guy also became non-negative. So when I decide on my pivot operation next, I've actually only got one more negative number to work with. That'll save us a bit of time, I think. Alright, here's our pivot column. Why? Because minus 2,000 is the only negative number left. I have to take these values and divide 1/2 into them, so 10 over 1/2, that's 10 times 2 is 20. 5 over 1/2, that's 5 times 2 is 10. 10 is the smaller value, so this is my pivot row, meaning 1/2 is my pivot entry. X1 will be my entering variable, S2 is my exiting variable, and now we just have to go through the motions. So first thing I want to do is rescale this. I want to make this a 1. So we'll do 2 times row 2 becomes our new row 2. Let's see. First row stays the same, 1/2, 1, 3/4, 1 over 2,000, 0, 0, 10. Multiply this row by 2, I've got 1, 0, 1/4 times 2 is 1/2, minus 1 over 2,000 times 2 is minus 1 over 1,000, 1 times 2 is 2, 0, 5 times 2 is 10, and third row stays the same, minus 2,000, 0, 0, 12, 0, 1, 240,000. Once again, because I have to erase this, I'm just going to keep track of these variables really quickly. And this was my entering variable. And all we have to do now is zero out these entries, and we should be done at that point. So, how do I do that? Row 1 minus 1/2 of row 2 becomes our new row 1. and we're going to do row 3 plus 2,000 times row 2 becomes our new row 3. Again, just going to check for copying errors. Everything looks okay though. Everything looks okay, so we'll proceed. Alright, let's see. Row 1 minus 1/2 of row 2. Well, actually, that's copying out row 2 really quickly. Because this one isn't being affected. Okay, row 1 minus 1/2 of row 2. 1/2 minus 1/2 times 1 is 0, just like I wanted. 1 minus 0 is 1. 3/4 minus 1/2 of 1/2. 1/2 times 1/2 is 1/4, so 3/4 minus 1/4 is 2/4, or 1/2. 1 over 2,000 minus 1/2 of 1 over 1,000. Well, that's 1 over 2,000 plus 1 over 2,000 is 2 over 2,000, or 1 over 1,000. 0 minus 1/2 of 2 is 0 minus 1 is minus 1. And 0 minus 0 is 0. 10 minus 1/2 of 10, so that's 10 minus 5 is 5. And now we're down to the third row. I've got minus 2,000 plus 2,000 is 0, just like I wanted. 0 plus 0 is 0. 0 plus 2,000 times 1/2. 2,000 times 1/2 is 1,000, so that's 0 plus 1,000. 12 plus 2,000 times minus 1,000. 2,000 times minus 1 over 1,000, I should say, is, that's minus 2,000 over 1,000, or minus 2. So 12 plus minus 2 is 10. And then I've got 0 plus 2 times 2,000 is 0 plus 4,000. 1 plus 0 is 0. Or sorry, 1 plus 0 is 1. And 24,000 plus 2,000 times 10. 2,000 times 10 is 20,000. 24,000 plus 20,000 is 26. Oops, my units are all wrong here. 240,000 plus 20,000 is 260,000. What did I have? I had x2, s1 was my exiting variable, x1 is my entering variable, so x1 replaces it. And here is our final simplex tableau. Why is it final? Because there's no negative numbers left on the bottom, so we're done. And I can read off my solutions. My solutions are x1 equals 10. x2 is the first row. x2 equals 5. And everything else that doesn't appear, so my slack variables and x3, those are all 0. So x3 equals 0. And this means my slack variables s1 and s2 are also 0. And p, my maximum number of viewers, is 260,000. And there's the answer. So remember what these corresponded to. x1 was the number of daytime hours, or number of daytime ads. So we want 10 daytime ads, 5 primetime ads, 0 late night ads. And if we do that, we will reach a total of 260,000 people. The simplex method is a long algorithm, but it takes me a lot longer to do it on the board than it will take you on your own, just because I have to explain it as I go through this process. But at least once, maybe twice filming this video, I have made copying errors. We've fixed them as we've gone through it, but be careful with that. It happens all the time. So always double check your work. And if you want to see more examples of the simplex method, the next section, 6.3, we will do basically the same thing with one additional step before we get going. So if you want to see more simplex method examples, we'll do more in the next video. There's also a ton in the textbook, so we'll stop here.